This beautiful image was created by NOAA Visualization Lab. We all recognize what this is. It plots known trajectory of all the hurricanes in the past. But we can't really recognize where the Florida is because we have so many of them. I took this from CNN. There's a lot of interest in hurricanes because of recent Harvey and Irma. It shows a direct hit from all the past hurricanes. You can see that we're hit by 117, the most recent one being Irma, and the next states are in the 50s, so we are hit more than twice by any other states. All those coastal states, hurricane is a serious issue, and of course, more so for Florida, as you can see from here. We just had one. And as we talked about just now, kids were hit really hard. And is there any laser pointer?
Yeah, it's at the very top on this thing right there.
So this image is taken right after Hurricane Irma. It shows the area image of the kids in the Big Pine area. They're still working on the numbers, but Harvey and Irma, they're estimating at about $70 billion insurance loss. And we know that the actual loss, that's only insured properties. So we know that actual property loss and economic loss is a lot greater. And they're estimating at about $250 billion. So it's a big hurricane. But when I see that as a structural engineer, and I hope you recognize that too, I see something interesting. So I see that the house on the bottom left is almost gone, except the concrete foundation. So this is entirely destroyed. Whereas I see a few other houses where we have roof shingle loss, roof sheeting loss. Probably the left side of the house here has a lot of water damage, but otherwise the house is intact on the other side. Whereas I see a home with only minor shingle loss and a few houses without any loss. So as structural engineers, we know that this heavily depends on how good building material that you use and how strong hardening measures that you take. This image is taken from previous studies in Australia. They actually were hit earlier than us. For us, the awakening moment was Hurricane Andrew in 1992. But for them, there was a tropical cyclone Tracy, 1974. So that was over 15 years earlier than us. It sort of wiped out certain part of Australia. And they, earlier than us, improved their building code. So we see from what they actually learned. This chart was created from insurance claims. And we can see clearly that the solid line prior to building code change and the dotted line after the building code change has a substantial reduction. The y-axis is the claimed loss, so substantial reduction in the loss. So we all know that this is really good. Hey, let's use better building material. It's gonna better survive the hurricane. But the big question is, how do we get there is the big question. It is an extremely complicated issue. It involves regulation, it involves consumer behavior. We couldn't possibly focus on all these aspects with a single project. So we sort of zoomed in using the collaboration that we established on the premium reduction opportunity. And we understand that the premium reduction doesn't happen overnight. If it happens overnight, we don't have any of these issues, but it happens so much slowly, so that's limitation. But on the positive side, premium reduction can reach out to a large number of houses. And so that's where we focused. So we had, I am from civil engineering. I had a collaborating professor from industrial engineering and 2 students from each of our department. Our collaborator, the end user, was CoreLogic, formerly EcoCat. It is one of the top three companies providing insurance risk analysis to smaller insurers. So we collaborated together to explore opportunities. So using a hypothetical number, let me use hypothetical numbers to illustrate where we want to go toward. This chart flat insurance claims from certain hurricane, and I want you to focus on this red box. So if you look at this red box, the x-axis is wind speed. So it's insurance claims at certain wind speed. Y-axis, of course, is different insurance claims. And you can see that there's a lot of scatter in this data. The way the insurance industry grouped the data is very simplistic as of now. The current state is very simplistic, and here's some hypothetical numbers to illustrate the point. If we have 3 different houses, and if all the houses are built around 1990, if all the houses have gable roof, what will happen even if there's a lot of scatter in the potential damage like this? All of them will have exactly same data group with the current practice, and therefore all of them will have exactly same premium. So we wanted to try to break that cycle. How we want to move toward is shown in this following table. Suppose one of the 3 houses was really built well, and I labeled it as a gable S, meaning that gable roof house strong building component. Then it's very likely that that house will suffer a lot less damage. So expected loss here is $30,000, whereas other houses are not as strong, and we have higher expected economic loss. So this is where we go toward, and the research is a component necessary to get there, was our research project. So in the long run, if this research effort, of course, it cannot be only this project, but if this group of research project is successful, in the long run, we hope that all of us will win as follows. First, homeowners will be rewarded by taking a good behavior, by using good building material, by taking good mitigation actions. They will be rewarded by the good behavior. As a nation, what will happen is more and more homes will be mitigated. So as a nation, instead of saying $50 billion after a certain hurricane, hopefully in the down the line, we'll see maybe $20 billion insurance loss. Insurers can be a winner too here, because if hit by hurricane, they don't have to pay out as many insurance claims. They can just respond to those damaged houses, which hopefully will be a lot less. All right, so that is overview of the benefit of a project like this. I understand the majority of the audience is from other disciplines, so I took out a lot of technical details. I'll just explain the overview of what we have worked on. So the first part was data collection, different capacity model. So basically what we did was we collected data and we differentiated stronger building components versus weaker building components. And then we created fragility model with bounds. What that is it shows probability of failure, if you will, how likely it is to fail. And then with that, we integrate all the building components and we'll be able to conduct loss estimation. So that's the overview of the work that we have done. And I just will share just a couple of examples, and just so that you have an idea of what we've worked on. So this is in the component level. So in the component on the left is toenail failure probability, not used anymore, but they tend to fail really early. You can see that failure wind speed is much lower here, whereas newer better components, the failure wind speed is much higher. So we want the consumers to use the component on the right. We first compiled many different building components. We created functions like this, and then we put all of them in this flowchart. This flowchart has a lot of boxes because it has a lot of building components. But what this box does, it estimates failure probability of a building. The rest was done by our end user. It was not possible to finish everything on our own within 2 years time frame of SEED's grant. So they have this hazard module where they have over 30 probabilistic storms with different paths and different strengths. So we utilized their hurricane storm model, and then building component was our work. financial module, the last box, we also relied on their expertise. So we put everything together and we ran many different scenarios. And here is one sample scenario that we analyzed. Of many scenarios we have, this is one that I wanted to share with you. So the contour shows annual average loss, expected loss. For the weak component on the top, you can see that the color is generally darker. Whereas for the strong component, you can see that it's a lot lighter color, meaning we have a lot less expected damage. And here's actual numbers that created the figure. So I am plotting here the top 5 counties that have highest expected loss. The table has 3 different columns. Weak represents what will happen to weak house, average annual loss. And that's actually, by the way, percentage of the house value. And average house is the next column, and strong house is the last column. And you can see that for all counties, as you move from weak building component to the strong building component, the failure probability goes down a lot. And the last row shows the analysis for the entire Florida. So we created scenarios like this, and we delivered them to our end user. And so in order not to limit our findings to only our end user, we also published this to a paper where the audience includes those companies. So I just wanted to reiterate the role of the end user in my last slide. The end user, like CoreLogic or RMS, Air, Worldwide, they provide risk analysis to insurers. A lot of smaller insurers, or even big ones, don't have technical expertise to analyze this accurately. So these companies, like our end user, provides risk analysis as shown in this figure. I took this figure from CoreLogic webpage. It shows different risk levels and premiums that they recommend to the insurers, smaller insurers. So our goal was to inform the risk analysis company so that they can utilize the information that we provided them in conducting their business. So that's my last slide, and I'll be happy to answer your questions at the end of the session. Thank you.